Okay, so this is lesson 4.2. We're going to learn how to compare functions. It's important to look at the slope. All right, guys? Slope is really just the rate of change, and it describes how one quantity changes in relation to another. So you guys have worked in science like speed, right? You've done some stuff with some labs where you've actually used a stopwatch to keep track of the time and how long something takes to do whatever, right? So you're comparing two quantities, and that's really just slope, all right? So in math, what we get is sometimes an equation, okay? These two equations are both linear equations because they're in the format y equals mx plus b, remember that? So if you know the equation is already in slope-intercept form, y equals mx plus b, we know that the slope is the m value. So in this equation, wouldn't you agree that 2 is your slope? And that might mean 2 miles per hour. It might mean $2 per item. We don't really know necessarily without any context or in a problem. That's why we're going to work on the stuff tomorrow that deals with the superheroes. Because the superheroes are either going to be like fighting enemies or they're going to be competing against each other somehow. So it'll give you a little more context than just a generic B. Yep. So the thing to remember is you do have a y-intercept in your equation as well. Your y-intercept doesn't necessarily tell you about the slope, right? It kind of gives you a starting point. So we had talked earlier about different equations that were either proportional or non-proportional. Would this one be proportional since its y-intercept is 5? What did we say proportional equations had to have? Goes through 0, 0. This one, if you were to graph it, has to start up here at 5, and then it's going to have what kind of slope to it? Positive. So if you remember a little bit about graphing, this one would kind of look like this when you sketched it, right? Y equals 2x plus 5 would look like that. The other equation example that I gave you is still linear. Do you guys remember what we talked about? If you get an equation that looks like this, but it's kind of messy, do you remember what we do to it? Yeah, exactly, okay? Your job is to get it to look like this one. We wanted to say y equals. So you're allowed to use some algebra. I drew in the locker to hopefully remind you. But if we do some algebra, do you guys remember how you can move this 3x over? Right now it's positive 3x, right? So if you subtract it from both sides, you've officially moved it over here so it can sit next to the 12. See how it already kind of looks to be better than what we started with? It already has the y term by itself on the left. So what do we have to do to actually finish, though? What do we do to finish it up? Yeah, okay, close. Negative 4, okay? If you have a coefficient in front of your y term, we always said that to get rid of it, you would divide by that number, even if it is negative, okay? The reason you want to divide by a negative is so that that cancels clean, and you end up with plain old y equals. And then on this side, is it always going to clean up nice to give you a whole number? Okay, what's going to happen is a negative divided by a negative can turn positive, but you're often going to get a fractional value there, okay? And that's not going to be an issue because, guys, you're used to dealing with slope being a fraction, right? Back here, you want to make sure you do divide it out. And that will typically end up to be a whole number. Not always, okay, but it typically will. So what do you know about this one? You know its slope is 3/4. Y is 3, run 4. You know its y-intercept this time is negative 3, right? So if we were to sketch this one, it's going to cross down here at negative 3. And guys, is it going to be steeper than the other one? Think about rising 2, running 1. And then this one has rise 3, run 4. What's that going to look like? Your run's a little longer, right? So what would you say about these two functions? Is one steeper than the other? Should be, right? Wouldn't this be steeper, rising 2 and only running 1? Okay, so sometimes comparing the two things that we have is really easy when you have a graph. It's not always as easy when you just have an equation. So a lot of times you have to look at the numbers and compare them. Is 2 greater than 3/4? Well, yeah. 3/4 is 0.75, right? So 0.75 is going to be a smaller value than 2, and that's how we know it's going to be less steep the smaller number we get for our slope. The bigger number is going to be a steeper line. Make sense? Okay. So guys, what if we don't have a full-blown equation? What do we do if we just have a bunch of points in front of us? Can we still find the slope? Okay. We can use our slope formula. Okay. Guys, do you remember the critical part of using this formula, though? Because I have a lot of kids who start out just doing this. And please don't write this down because this is so wrong. Okay? You cannot just take the numbers in the formula and start throwing them in, or the numbers from the points and start throwing them in. Okay? So do you remember what was crucial about setting this up? Right. So here's the thing. If you have 2 points sitting in front of you, what should we do to kind of organize ourselves before we begin, though? Anybody remember what we did?
I know the answer, though.
Okay, and that's good, because some kids can see it because they're used to doing it, okay? But here's what I found. If you have 2 points, okay, what I want you to do is I want you to label them. This is your first point. Every point has x and y values, right? So this is going to be x1, y1. And this is our second point. It's going to be made up of x and y values also. So make sure you label it x1, y1, the first point, and then x2, y2. Now you can grab your formula. We want y2 minus y1. Here's y2. Here's y1. Okay, you do need the minus sign and the -2 when you're doing this, when there's negative numbers, right? How about on the bottom? We need x2 minus x1. Be careful with your symbols. Or with your signs, minusing a negative really turns into, yeah. So we have a slope of 10. That's a really steep line. Whoops. I got 2 extra lines on there. I don't know what's going on with my board here, guys, but try it again. So anyways, how about the second one? No negative numbers. This one should come out a little bit nicer, shouldn't it? Where do we end up over there? -3. Let's see. x1, y1, x2, y2, so you're going to start out with 10 minus 1, and then 2 minus 5. So 9 over -3, be careful, turns into, it'll be negative, okay? So here's the thing, okay? Really steep. We already decided that first one has a rise of 10 and a run of 1. How about the other one? Still pretty steep, isn't it? It's going down 3 and then over 1. So it's still pretty steep, but who is definitely steeper? Okay, we would say this has the greater rate of change. Not that it's positive, but that it's steeper than this one. This one's still pretty steep, right? But it's headed downhill. Okay, so try to always picture in your head, too, when you have to compare 2 functions, what they're going to look like. And if you want to sketch it, you can. Okay, there's no reason why we can't sketch it like we did with this one up here. All right, so on the other side, we get some tables, okay? Some of us are better than others looking for the pattern, right? So we talked about how you can always compare the change in y to what's happening in your chart, and then compare the change in x, right? The only problem is that sometimes confusing when you're looking at a table. So a lot of times I just tell students, you know what, you can still use this formula. Just pick the bottommost 2 points, right? And you can look between those 2 points and always get your slope. So let's see, if we do these 2, and this is x1, y1, x2, y2, and let's see, that's really messy now, but I guess we'll go with it. My slope is going to be y2 minus y1, x2 minus x1, and I think we get 6 over 2. Can that reduce?
Yeah, 3.
Yeah, so slope of 3. Did anybody notice the pattern? See how it goes up by 6 in the y column, and then it goes up by 2? Some people can go right to this formula right here. Change in y was 6, change in x was 2, and then there's my slope. Can we do that when the table's going sideways? Yeah, just be careful. This is going to be your x, this is going to be your y. So if you're looking at the change, like we talked about, when you just want to do a pattern, is there a clear pattern that we can see going from 4 to 12, and then 12 to 20, and 20 to 28? Yeah, it's going up by, careful. The change in y values, right, is the pattern that we see. It means it's going up by 8, okay? Is the x values also going up by 8? Okay, so you'll notice that the x pattern is going up with a change of 2. Okay, so see how we can sometimes use the table to look for the pattern instead of always going for your formula? Did anybody go ahead and grab these last 2 points and use the formula? Do you still get 8 over 2? Awesome. So reduce it. Who has the greater rate of change? A or B? Or wait, I guess I used E and F. E has a change of just 3. Remember, rise 3, run 1? It's steep. But isn't this going to be steeper? Rising 4, running 1 is going to have the steeper slope. Very good. All right, so I saved the easiest for last. It says when you have a graph, you want to pay attention to the rise over run. You guys remember that formula, right? When you look at the rise over run, it is kind of crucial that you do one thing first. You need a couple of good points. Okay, remember the tiles on the floor? Where they come together, that point in the middle is a good point that you would pick when you're looking at a graph. So I think with this one, it looks like we have a really good y-intercept right there. Would I want to pick this next point right next to it? Or even this one right here? Yeah, see how they're kind of out in the middle of nowhere? You want to go to where the grid lines cross. So that right there would be a good set of points to pick to do your slope triangle. And then look at the, always look at your labeling. Okay, do we go up by ones? Do we go over by ones? Because if you don't, you really have to pay attention to that because that can change, right? The scale changes. It looks to me like it's just rise 1, run 4. Okay, that's not a very steep line, but that's okay. Sometimes they don't have to be steep. How about this one? This one gave us a nice point right there, so I'm going to use it. Now, I can count boxes. That's up 3 over 2. But is it really $3 for 2 miles, according to the labeling? No. What did they do to their scale over here? Yeah, they kind of went by tens every other. So if I go up 3 boxes, that really means 5, 10, 15 is my rise, and 2 miles. So how much is it per mile? 15 for 2 miles. So that means if I reduce, I get $7.50 per mile. Remember earlier we were talking about using the context of the problem? If they give you labels on your scale, that's what it means. You're going to pay $7.50 per mile, or maybe it's a fundraiser and you're going to raise $7.50 per mile. Okay? Out of the two, obviously, which one has a greater rate of change? Which one's steeper? Definitely this one. Okay, it came out to be $7.50. This one only came out 1.4. So that would be like, if you use the same units, this would be like 25 cents per mile, right? Okay, so definitely greater rate of change over here once you pick it apart. All right, so I don't think I took a picture of my book, but I think you guys know what to do. You're going to cut down the center. You're going to tape it in front of the notes that we did on Friday, which I believe was lesson 4.3. All right, leave room for 4.1 still. We'll do that later in the week.